Now let's focus our attention on relativistic dynamics. Is Newton's second law still valid in relativity? And if so, do we need any modifications? What about the concepts of energy, momentum, and so on? Let's take a closer look. Newton's second law states that the external force exerted on an object, on a system, F external, equals to its rate of change of linear momentum. Now suppose we keep this still valid in relativity. Do we have to make any modifications? In other words, is P still the same as mv, or mu to be exact, u being the velocity of an object with mass n moving in a reference frame S. If P remains equal to mu, with m being the fixed mass of that object, then of course F external becomes mass times acceleration, okay? Because as we learned before, this is just d dt of mu, and since m is a constant, I can take it out. What's left is du dt, or a. But there is a problem here. Unlike Newton's classical mechanics, in which there is no upper limit to any speed, now we have an absolute upper limit to any speed, and which is the speed of light. So suppose we have a constant force, no matter how small it is, okay? If we have that constant force, and we keep on pushing and pushing and pushing on an object, if we give it long enough time, we're going to get a constant acceleration, and eventually the speed of that object will be exceeding the speed of light, right? Because the speed is equal to acceleration times t, and acceleration being a constant. If t is long enough, the speed u is going to exceed the speed of light. But we know that is not true in relativity. So to be self-consistent, we cannot keep the same definition of P equals mu, with m being its fixed mass. Rather, we have to somehow modify it so that as the speed of the object approaches that of light, the acceleration must reduce to 0. So therefore, P is not equal to mu anymore. So how do we make that modification? Well, our hunch actually comes back from classical physics, because in classical physics, we know that the mass is the quantity of inertia. It is the quantity which defines its ability to resist acceleration. The greater the mass is, the smaller the acceleration. Now, since we have a threshold of speed that we cannot cross, which is the speed of light, as you try to accelerate an object, as it goes faster and faster and faster, as it approaches the speed of light, it can no longer accelerate, which means the acceleration goes to 0. And what can we say about the mass? Well, the reason why the acceleration approaches 0, no matter what kind of force you apply, is because the mass must be very large, right? In fact, the mass approaches infinity. So we conclude that to be self-consistent, the mass m in the definition of momentum in relativity must increase as the speed of the object increases, and it must approach infinity as u approaches c. So we're looking at the mass, which starts from its normal non-relativistic value at low speed and gradually reaching infinity as the speed approaches that of light. Can we achieve that by multiplying m by a certain factor? Can we do that? M becomes what? Well, this factor is such that it equals 1 at low speeds, because you have to go back to classical physics, and it approaches infinity at u approaching c. Have we seen a quantity like that? Oh yes, we have been using this quantity a lot, and that of course is gamma. Gamma. Because gamma indeed starts from 1 at low speeds and approaching infinity at the speed of light. So is it possible for us to make this simple modification, taking m as gamma times m, and therefore P would become gamma mu? Can we do that? That seemed to solve the problem, at least, of the speed of light being the highest possible speed, right? Because as the speed u approaches that of light, gamma approaches infinity, so the effective mass which is gamma times n, approaches infinity, you cannot possibly accelerate a mass of infinity. No matter how much force you apply, it will never increase the speed anymore. This tells us the speed of light will never be broken. So that is our hunch. Is it true? Well, let's use the following example to check whether this argument makes sense or not. In classical physics, one of the most important reasons why we introduced the concept of linear momentum is because under the right circumstances, it is conserved. When is it conserved? Well, that's when external force equals 0. Conservation laws are the crown jewels of physics, and we do not expect to lose any conservation law as we go beyond classical physics. We expect conservation laws to hold true in relativity as well. So we expect to get still conservation of linear momentum when the external force on a system is 0, even in relativistic case. And when we studied linear momentum in Physics 1A, we often used a collision to demonstrate conservation of momentum. In the collision process, the force between two objects engaged in collision is internal if you treat both objects as part of the same system. So we were able to apply conservation of linear momentum. Now let's consider a collision with relativistic speeds. I have here two objects, a red ball and a green ball. The red ball is called A, the green ball is called B. And here's what I'm going to do. I assume that these two balls have exactly the same mass. They're actually identical. They're identical. And in the reference frame S, I throw this ball in the y direction only with a speed u. Okay, so it moves upward with a speed u. Now, what about the other second green ball, B? This ball moves along the S prime frame, which means relative to S, it is moving with a constant velocity of v along the x-axis. But meanwhile, a person in the S prime frame also throws this green ball downwards along the y prime axis with a velocity which is equal to the negative value of u. So according to the observer in S prime frame, this ball goes downwards with a velocity of negative u. Okay? And if you throw it at the right moment, these two balls will collide. And after they collide, each will rebound, and that's the end of the collision. Now, in classical physics, when you have two identical masses in a complete elastic collision, what is the result of the collision? Well, the result of the collision is that they're going to exchange their momentum, right? P1 becomes P2, P2 becomes P1. And if you look at classical physics, in this case, the collision happened in the y direction. The momentum in the x direction does not change. The total moment in the y direction also does not change as a result. And that makes sense because they both have mass m. Okay? Remember, in classical physics, the mass m does not change. And the first ball goes upward, so it's got a positive momentum of mu along the x direction. Okay? So PA initial equals mu positive, and PB initial equals negative mu. Okay, the velocity is negative u in the S prime frame in the y direction. It is also negative u in the S frame because the difference between S and S prime is only the movement in the x direction. There is no relative motion between the two reference frames in the y direction. So both observers in S and S prime will agree on the whatever measurement in the y direction, the velocity. So it's negative mu for both S and S prime. So you see here, you add them together, you get 0. So P initial total is equal to PA initial plus PB initial. I'm looking only at the y direction, by the way. Okay. Of course, in x direction, there's no exchange of momentum of any sort. So that is equal to what? That is equal to 0. Mu minus mu. That is the momentum before the collision. Now, after the collision, they simply exchange their momentum. And that result is still 0. Okay? Sigma p final. It is still 0. We still clearly have conservation of linear momentum. That was the classical case. Can we say the same thing? Can we analyze the situation for relativistic case? That is, you consider these two balls to move at relativistic speeds, and therefore you have to use relativistic velocity transformation. Can we still apply conservation of linear momentum? Well, we better hope the linear momentum is still conserved. That is the whole idea. We want to preserve the conservation of linear momentum because there is no external force on the system which consists of these two objects. What are we going to find? First of all, let's try not to change the classical formula for momentum. We still assume that P equals m times u, m being its constant mass. If we did that, can we still preserve the conservation of linear momentum for this collision? Well, let's see. If we have to use relativistic velocity transformation, what result are we going to get? Well, before the collision, for ball A, I have UAX equals 0 and UAY equals positive U. That's measured in the S frame. Okay, and what about ball B? Well, for ball B, measured in the X prime frame, S prime frame, I have UBY prime. Okay, I have to use prime because in S prime frame equals negative U. Remember I said in the S prime frame it's negative U, but in the S frame it's a different story. Okay, in the S frame I know only that UBX in the X direction it's V because there is no motion in the X direction for this ball, the green ball B, relative to S prime frame, but S prime frame moves along this direction with V, so the ball must follow with the exact same velocity, so it's V according to the S frame. What I want to do is to observe this collision in S frame. So I'm going to change this UBY prime to UBY, which is measured in S frame, not S prime frame. So I have to do a relativistic velocity transformation. So how do I do that? In other words, what is UBY? UBY equals dyB dt, right? dyB dt. Now, I know that dyB is simply equal to dyB prime because Lorentz transformation says the y direction, there is no change in coordinate. But I have to, if I go from dt to dt prime, that's a different story. T and T prime are not the same in different reference frames. Remember that? Lorentz transformation. So what do I say here? D of, I am going to change T to T prime. And remember, this is T to T prime, not T prime to T. So there is a plus and minus sign issue here. So remember the Lorentz transformation, if I go backwards, I get gamma times T prime plus Vx prime over C. Now, if we continue this calculation, let's see what we get. This is dyB prime. And then gamma is a constant, because V is a constant, I'm going to take that out, dt prime. And what's left is V dx prime over C. V dx prime over C. What is dx prime? That's the change in the coordinate of this green ball B according to the S prime frame. And what is that? That is 0 because it doesn't move along the X direction in the S prime frame. Remember that? So this is 0. Okay, this is 0. So I can get 1 over gamma, which I copy from here, dyB prime dt prime. dyB prime over dt prime. By definition, this is the velocity of this ball measured in the S prime frame in the Y direction. UB prime. Y. But wait a minute, I know what that is. That is just negative U, right? So I can write this as negative U over gamma. You see here, I have a new factor here, gamma, which did not exist before. That is telling me that the velocity of this green ball B in the Y direction, even though it's equal to negative U according to S prime frame, it is not the same according to observing in S frame. It differs by this gamma factor, and we actually know where that comes from. That is because these two reference frames have different clocks. So even though it moves the same distance, that did not happen in the same time move duration. So therefore, there is a gamma factor. And is there something wrong with this? Well, it turns out, yes, there is something wrong with this. Because before the collision, A goes up, B goes down in a y direction. After the collision, they got just reversed. The directions of motion reversed. Now you know from classical physics that if you got two identical objects in a complete elastic collision, they're gonna just rebound. So u becomes negative u, and this negative u becomes positive u. So both momenta get reversed, and the sum remains zero, just like before. But what we have here is the red one going up and the gray one going down with different amount of linear momentum. They don't just differ by negative sign. In fact, this ball, the red one, goes up with a momentum of positive mu, but the green one goes down with a momentum of negative m times u over gamma. Gamma is not equal to 1, so they are different, which means that the momentum of the system in the y direction before the collision was not actually equal to 0 if you add these two momenta up. So let's write down this observation. The momentum of the two-ball system before the collision in the y direction does not sum up to 0 if you consider relativistic velocity transformation because of its actual factor gamma. Is there something wrong with this? And you bet there is something wrong with this, because as a result of the collision, both balls will simply reverse their momentum. So the first ball will have a momentum of negative mu, the second will have a momentum of positive mu over gamma, and then this tells us that the final momentum of the system is negative of that. And not only is that not equal to 0, it in fact equals the negative value of this. Now, any non-zero quantity, if you add a negative sign, it's not the same anymore, right? And therefore, we say that the momentum in the y direction is not conserved. How can that be? There's something wrong with this. And that is because we made the wrong assumption. The assumption was we could still define momentum as the mass of the object, which is a fixed quantity, times its velocity. And we already saw that was not possible because of the speed of light threshold. But now we also saw that if we did that, we wouldn't be able to conserve momentum in this particular case, even though the external force is 0. So, is it possible then that when I add back that gamma factor, according to our hunch, we add that gamma factor to the mass, we'll multiply this mass by the gamma factor, is it possible that in our example, we will be able to conserve linear momentum? Well, that's what we're going to find out. As a matter of fact, the problem with here is that the initial momentum was not 0 for the two-object system. And you reverse it, you're not going to get the same quantity anymore. If we can somehow prove that with this additional factor gamma, the initial momentum of the two balls cancel each other out, which means the total initial momentum of a two-ball system was 0 before the collision. Then after they get reversed as a result of the collision, it'd still be 0, which means it's still conserved, right? 0 equals 0. I don't care if we add a negative sign. Okay, so this is what we're going to set out to prove, and that is, with this additional factor gamma, the initial momentum of the two-ball system is 0. Let's try that. So let's see now. Before the collision, according to our new definition of momentum, we must multiply the mass with a gamma factor. This gamma factor uses a speed u, which is the speed at which the object moves relative to a certain reference frame. So for ball A was moving with a constant speed u upwards in S frame before the collision, so it's gamma u mv. I put a u here to indicate that when you calculate gamma here, you have to use u for the speed. So m times u, that is the original expression for momentum. I just multiply this by gamma u. Now, the momentum for ball B before the collision, that's a little bit more intricate. First of all, its original mass is m. I have to multiply this by gamma u prime. What's u prime? U prime is the total speed of that ball in the S frame. In the S frame, because I measure everything in S frame. Okay, since it moves with that speed, I have to enhance the mass with that factor. And that speed, the corresponding velocity, has two components. Remember, we're measuring the motion of ball B in the S frame before the collision. In the S frame, it is moving at a constant speed v in the horizontal direction, and it is moving at a certain downward velocity in the y direction, and we already figured that out. That's negative u over gamma. Remember that gamma factor we just saw a minute ago? And that gamma is not the same as this one or this one, because that gamma, we got that by Lorentz transformation. That gamma is in fact using v, the speed between the two reference frames. Okay, so we have to add a little subscript here for clarification here. So it's gamma v. Okay, I just want to show that besides this negative sign, these two momenta before the collision have the same magnitude. Since one is positive, the other is negative, they're going to cancel out. They're going to add up to 0. And since the total momentum was 0 before the collision, after the collision they each get reversed, the sum is still 0, so we're happy. Okay, so is it true that the initial and final initial momenta of this one and that one have the same magnitude? I'm just ignoring the negative sign here. Is it true that PAI, absolute value, equals PBI? If we can show that, then the conservation of linear momentum would still hold true in this relativistic case. That means we have to equate this with that without the negative sign, which means gamma u mu must equal to gamma u prime u over gamma v times m. Let's cross out m and let's cross out u. This is to say that gamma u equals gamma u prime over gamma v. Now let's move that gamma v over gamma v. Must equal to gamma u prime. Is that true? Well, that's what we're going to see. And it turns out, well, to see that, all we need to do is substitute the expression for gamma u, gamma v, and gamma u prime. This, as you know, is gamma u, and this is gamma v. Now, gamma u prime, you have to be a little bit more careful because you have to use u prime for the speed, and the u prime, the velocity, has two components. Here's the x direction, v. Here's the y direction, negative u over gamma v, which you already calculated. So this is 1 minus u prime squared, which is, by Pythagorean theorem, this squared plus that squared. So it's v squared plus negative u over gamma v, the whole thing, squared, and then you divide it by c squared. So if we plug in the expressions for gamma u, gamma v, and gamma u prime into the identity we wanted to prove, and don't worry about the square root and this numerator denominator, we can just square everything and just flip over the numerator denominator, we come up with this. So is this true? Well, yes it is. First of all, we take that 1 minus v squared over c squared, leave it here. What's left is minus u squared over c squared times 1 over gamma v squared. Now gamma v is this, right? So if you square it and flip it over, don't you get this? This is 1 over gamma v squared. Right? Now you have a 1 over v squared over c squared and 1 over v squared over c squared. You take both of them out. What's left is 1 minus u squared over c squared. And these two sides are indeed equal to each other. You can see here. So that tells us that our original assumption, this was right, this is right, and this tells us, indeed, as we add this gamma factor to the mass, we will find that before the collision for this particular situation, the linear momentum in the y direction for the two-ball system added up to 0. So as they flipped signs as a result of the collision, the total result remains 0. We have restored the conservation of linear momentum in this case. So this example gives us further evidence that it is indeed correct to modify the expression of linear momentum by adding this gamma factor. Let's conclude. We conclude that the relativistic linear momentum should be defined as such: gamma times m times u, and this gamma is the gamma factor for a speed u. It's given by this. This expression not only guarantees that nothing can ever exceed the speed of light because the mass would approach infinity as you try to approach the speed of light, and also guarantees the conservation of linear momentum to remain true for an isolated system with no external force. Now, what if you have an external force? Then the momentum will change, just like in classical physics. And the rate at which the momentum changes, it's still the external force. So we preserve Newton's second law by adding this additional factor, the gamma factor. And the expression for relativistic momentum, how does it differ from that of classical expression, which is just m times u without the gamma factor? Well, we can take a look at this graph. If I plot linear momentum as a function of the speed u of the particle, in classical physics, p equals mu, m being a constant, so you just get a constant slope line, which is just a straight line whose slope is just m. It never changes. And u can be as large as infinity if you keep on accelerating it. But in relativistic case, there is a threshold c, which is the upper limit of the speed, and the relativistic momentum approaches infinity as u approaches c because this gamma factor. This is the difference. So you see, at low speeds, they're almost equal to each other, but at high speeds, they start to differ a lot. As an example, let's find the acceleration of an object relativistically as a function of the force F. Normally, when you apply a force on an object of given mass, you're going to get a given acceleration. But relativistically, since the effective mass increases as the speed increases, the acceleration will be less and less as the speed picks up. So now the acceleration is not only a function of the mass, or the original mass and the force applied, it is also a function of the speed. Let's find that out. We start with the relativistic version of Newton's second law, F equals to dp dt. And that, as we have learned, this P is m gamma u, with gamma being 1 over the square root of v, 1 minus u squared over c squared. So let me write this down. M is a constant, we'll take that out. ddt of u divided by the square root of 1 minus u squared over c squared. So I'm going to write this like that. And let's just go ahead and finish the derivative, shall we? Now there are two terms. The first term, I'm going to just take du over dt, which is a, and I'm going to leave that gamma factor as is. That's the gamma factor, 1 minus u squared over c squared. Now the next one, I'm going to keep that u as is. I'm going to take a derivative with respect to this gamma factor. So plus mu and ddt of this gamma factor. It's in the denominator, so it's to the power negative 1/2. So you have a negative 1/2, and then it's 1 minus u squared over c squared becomes negative 3/2 in the denominator. And don't forget, you also need to, by chain rule, take a derivative of respect to this thing itself inside the square root. And then it's 1 minus u squared over c squared. You take a derivative, you get negative 2u over c squared, and then du dt, which is a. So here I did one more step. I cleared this up a little bit and took out ma, and that's what I get. And all you have to do is combine these two terms together, and you find a quite simple answer. F equals ma divided by this. This, of course, is the new factor that we did not have in classical physics. And you solve for a, you'll find that a to be equal to F over m, which is its classical value multiplied by this extra factor. You recognize this extra factor is just gamma to the power negative 3. Okay? Gamma to the power negative 3. So the acceleration is not just equal to F over m, but you have to multiply this by this additional factor, 1 over gamma to the power 3. As you know, gamma approaches infinity as u approaches c. And of course, 1 over gamma to the power 3 would then approach 0. So as u approaches c, the speed approaches c, the acceleration indeed diminishes to 0. That is expected.